In this video, we will start talking about work. And in physics, work is defined to be force multiplied by distance. So work is always done by a force that acts on an object over a distance. Now, you may notice something interesting here. Work is not a vector. Work is just a number. Yet, force is a vector, and the distance over which it acts is also a vector. It's a displacement vector. So why is it? What does it mean? Why is it that I have two vectors and I multiply them together and I don't get one? And the best way I can demonstrate this is, let's say that you have a predetermined, so let's say a force is acting along a path. So an object is moving along this path. We'll say that this is D. And the force acted at an angle, F. Good. So this quantity right here, F times D, I'm going to actually, how about this? This quantity right here, F times D, will be this length right here. And stop. F, this is F times D. So how come I was able to determine that F times D is this? Oh, and by the way, F times D is just the length of this arrow. So it is the work, okay? It's just the length of this blue arrow right here. So let's see how I constructed this. If you think about F as a triangle here, notice how where I left off. F will be formed by a triangle of this this component of the force plus and this component of the force. So if you take this force, you break it into components, one along the direction that you traveled and one perpendicular to it, you find this, right? So let's say that there's an angle here, theta, right? So that angle here, theta, that means that this length right here from there to there is F cosine of theta, right? Okay, and if you look on your textbook, I'm going to go ahead and write this over here. If you look at your textbook, the definition for work from the textbook is work equals to force times distance times cosine of an angle. And this is the case if your distance and your force do not align, and they do not align by this angle right here. Okay, but the overall where this comes from is this multiplication of two vectors. Okay, you've seen this before. You have seen this before. There was a homework assignment in which there was a cart. So there was, okay, that's third time, right? Okay, there you go. There was a floor and there was a cart, right? And someone was pulling it with some tension right here. They were pulling it with a force this way. But you know that this cart was only allowed to move in this direction. In this direction. I think it was a nurse pulling a cart with some degree, some angle. I think it was 55 degrees or something like that. But you get the idea. What happens here is that this 55 degrees is this angle right there. And so you have to apply the cosine of 55 degrees to this force to figure out what the work would have been. All right. And as we do more examples in the future, you will see how to use this angle. I just wanted to go ahead and show you how this construction here works. Okay. So let's go ahead and look at another example. So let's say I have a level surface, and now I have a box. Frictionless, mass m, and it's moving with velocity v initial, going to the right. We're going to do work on this box. So what's going to happen now is there's no force acting on it. Then a minute later, right when it gets to here, so a little time after that, it's still v initial. But now we are going to apply a force F this way. And then after a certain distance, m over here, now we are moving with some different velocity this way, velocity final, and the force still there. And I wanted to note that this box traveled a distance, d. Right? Now, let's look at what it means to do work. So to do work is force times distance. And remember, we turn these two vectors into a number by looking at how their orientations are to each other. And the best way I like to do this is just go ahead. The distance vector points to the right, right? So this is the distance vector. Points to the right. And then the force vector is points over here. Great. So what is the angle here? The angle is 0. Cosine of 0 is 1. So the work here boils down to nothing but force times distance. But now I threw another concept in here, right? We are now looking at velocities. We had a velocity initial here and a velocity final there. So let's look at this term, the force. Let's open force up. As you remember, force equals mass times acceleration. So mass times acceleration times distance. Now, there is some hope here to bring in these velocities in. And why do I say that? This term is an inertia term, is mass. And these terms, these two right here, they're kinematics terms, right? So what I'm going to do now is I'm going to look at this motion that we described on the left in a purely kinematical way, meaning that we are not going to use mass whatsoever. No inertia, no mass, no Newton's laws, even before all of that. We're just going to describe the motion. Okay, so when we go ahead and do that, so if we go back to kinematics, this motion, and this is a review, and this is an acceleration does not equal zero motion, right? And whenever you have acceleration that does not equal to zero, the two equations that you ought to use is, the first one is that velocity final equals to acceleration times time plus velocity initial. And the distance relation equals to 1/2 acceleration times squared plus velocity initial time. Okay? We want to move away from using time here. If you notice, there is no concept of time here aside from this acceleration. This is a basic quantity, is mass. This is a basic quantity, is length, and this is a constructed quantity. So acceleration is deconstructed here. It's meters per second squared, so it's length over time squared. Okay. So let's see if we can tie the concept of work to the kinematics of the motion. So here what I'm going to do is this. I'm going to take this equation, solve for time, and then plug it into this one. So let's do it. Time here just becomes, let's see, velocity final minus velocity initial over acceleration. Good. And now, every time time shows up, we put that in there. Good. So then, if we continue with this idea, the distance equals to 1/2 acceleration. Now this whole quantity, velocity final minus velocity initial over acceleration, the whole quantity squared, plus velocity initial times time. Now this is also the whole quantity, velocity final minus velocity initial over acceleration. And it doesn't seem very promising at this point, does it? But let's massage this a little bit more. So I'm just going to carry out a couple more algebraic steps. I'm going to pull your attention that there is an acceleration here and 2 powers of acceleration there. There's a power of acceleration there, meaning that I can multiply both sides of this equation by acceleration. And you may say, why does that? Well, what does that buy me? Well, I don't have to keep writing accelerations over and over. And that's precisely what I'm going to do. So the left side then here becomes acceleration times distance equals to, we have, yeah, good, 1/2 velocity final minus velocity initial squared plus, in here you have velocity initial times velocity final minus velocity initial. So let's go ahead and complete this on the right side. So here we're going to have to open it, open this fraction, or this we have to open the square here. So this turns out to be velocity final squared minus 2 velocity final velocity initial plus velocity initial squared. And I'm going to just go ahead and distribute these. So this is velocity initial times velocity final. And this is going to be minus velocity initial squared. And at this point, a couple of interesting things start happening. This 2 here cancels this 2 there. So this is minus V final, V initial. But this is plus V initial, V final. So this term cancels that term completely. That goes away. So what are you left with? You're left with 1/2 of V final squared plus 1/2 of V initial squared minus 1 V initial squared. Did you get that? So just for sake of completeness, let me write this out, and let me change up a little bit. There you go. So this is 1/2 velocity final squared plus 1/2 velocity initial squared minus 1. This is basically 1 velocity initial squared, but 1/2 minus 1 is minus 1/2. So this really all comes back down to 1/2 velocity final squared minus 1/2 velocity initial squared. This looks a lot more manageable, right? This ties the final velocity and the initial velocity, and it ties it to acceleration times distance. So let's go back, let's pull our attention back to this. Note how acceleration times the distance, that's the kinematics of this. So work equals to mass times all the kinematics we hid in these 2 terms. But we were able to tie these 2 terms back to the velocities, right? Or the speeds, I should say. And they look like that. So let me actually write work then in the full form. So if you look back what work is and you look at what we have now, what you will end up with is that work is mass times everything we got here is 1/2 velocity final squared minus 1/2 velocity initial squared. And then I can distribute, and we can write it as 1/2 mass velocity final squared minus 1/2 the mass times velocity initial squared. This is hinting at some sort of change. So work is hinting at some change here. You have a final speed and a final minus an initial something. Now this something, this entire term here, is something actually very special in physics. This is kinetic energy, and more specifically kinetic energy final. And this one is kinetic energy initial. So if we define the work this way and we define kinetic energy to be this, then we can say that in physics, work is a change in kinetic energy. And kinetic energy in this case of an object is 1/2 its mass times its velocity squared. And this is the first type of energy you are going to see in this class. It's the energy to do motion. So far, we have been able to first describe motion with kinematics. Then we could model motion with forces. Then we said that there's this thing called momentum. It's an amount of motion. And now we're constructing a special quantity called energy. And you're going to see that energy can be exchanged in between types. And this is the first type you're going to see. It's energy to motion. So objects will have momentum, which is its amount of motion. And if an object is in motion, there will be an associated quantity called the kinetic energy, which is it's a completely different thing than momentum. And that's very important to keep in mind, that momentum and energy are different. Okay, and the one thing I do like to remind students the differences in momentum and kinetic energy is that momentum, first of all, is a vector, right? So momentum is a vector quantity. It has the information of the direction encoded in it. And if you look at just the dimensional analysis, or the units, this is kilograms meters per second, right? However, on the other hand, kinetic energy is a scalar quantity. By that I mean it's not a vector, it's just numbers. So when you are required to put a velocity here a speed is what is required. Okay, and to prove the point that these quantities are very different, this is a kilogram meter squared over second squared. So you have an additional power of the speed units here showing up. Okay. I think that should be enough for this video. We are going to continue to do more work on this, and the next thing we're going to do will be to do example videos with using this idea of work to solve problems. So we're going to use this concept that work is the change in kinetic energy. We're going to use the kinetic energy, and we're also going to use force times distance. All right, have a good day.